Now I will move to design, and here I will add all the design parameters in order to select the appropriate profiles for my building to get a safe design and also to meet the serviceability limited states, which are the deflection and the drift. So I'll choose the code. I'll choose 2010 to be compatible with the uh, load combinations I used before, and I will start with define parameters, and I will start with a parameter called method. So in this parameter, I will select which design method I want to use. So as I selected the design combinations to be LRFD, I will continue with LRFD approach, and I will add. So here I can see that method LRFD is added below. And after that, I will add some parameters that are related to my design. So just stay with me and to see which parameters are essential for my design. Okay, now I will come to these design parameters in order, and I will start with the beam parameter. So for this parameter, I need to design each segment in my model between two physical nodes depending on the beam end forces and the section properties at more than one location. Because, for example, if I have a tapered beam, the highest location or the highest section properties, the deepest section and the highest area, might not be that area with the highest, for example, axial load. It might be designed for the highest moment and shear, and the highest axial load might be at a different location along the member length. So for this parameter, this is for example only. So this parameter, it will ensure that the design will be performed at the ends of each segment, in addition to performing the design at 1 over 12 of the section length at stations, 1 over 12 of the section length. So it will divide the section into various stations, and it will perform the design at these various stations based on the properties of the member and the loads applied at that station. Because for sure the moment will be variable, the shear might be variable, the axial load as well. So it will ensure that the member is designed for the highest forces at the critical section. So I will add this parameter. I will add after current, which means that I will still be in the same folder. It's advisable not to open a new folder for each load parameter or design parameter. So I will now after current, and it's add now below the method LRFD. And I will assign this for all my building. The other option is to specify these locations of these member from the command. However, no need to do this. It's better to use number one. So it will divide any member into 12 stations, which is more than enough to get the highest loads along its length for the critical section. Okay, now I will go and add the CB coefficient. The CB is the coefficient used for the calculation of lateral torsional buckling for a flexural member. Chapter F. Let me go back to the design. So CB is the coefficient of bracing, which also is part of the equation for checking the critical stress for the calculation of the moment for lateral torsional buckling limit state. So this is the coefficient CB. The default is 1 and 1 is conservative as we said before. So if I want to follow a conservative approach, I will add CB value equals to 1. However, if I put 0, the program will calculate this automatically. Except when I have cantilever. When I have a cantilever, like the overhang, here I need to input CB equals to 1. So I will add the CB value equals to 0 at the members, all the members. However, for the overhang or any cantilever, I will ensure that the CB value equals to 1 because let me go back and show you from the code that CB value must be 1 when I uh, apply it for a cantilever or overhang. So it must be 1. And in general, CB equal to 1 is a conservative approach. So if I want to follow a conservative approach, I can add 1, or if I don't add it, the default value is 1. So I will add now here 0 and I will add 1 and apply the 1 value for the overhang or any cantilever. So here I will apply this, or let me select the structure without the overhangs and I will apply it. Oh, sorry, here I need to now toggle the assign, which means if I select toggle the assign, so as you see now, it removed the assignment from these members. Now I will select by inverse, and here I have these overhangs, and I will apply CB value equal to 1. Okay, so let's go to the next parameter I need to input, which is here the F ultimate. So other parameters, you can go through them. However, I'm giving you the parameters that will affect my design for a typical building. Some parameters are to be used for some types of members. Some parameters might be used for some special cases for some structures. However, I'm giving you the most important or what I need for my example here to use. So now I will use F ultimate and F yield. So F ultimate, depending on the material, I will choose it to equal 410 megapascal. So in kilonewton per meter squared, I multiplied by 1000, add, and the F yield, as I assign the material from the direct analysis, it was high grade. So I will use high grade for my steel. And I will assign this for all my members. In some cases, you might need to have two materials. For example, if I have hollow structural sections and the supplier of these sections, or if I can fabricate these sections in my factory, in case I'm a contractor or steel fabricator, or I need to ship them, and they are only available in a low grade. For example, a field will be 250 megapascal. So in this case, I need to separate the assignment of the material. So I will assign the high grade for all the built up or even hot rolled eye sections, and for the pipes and tubes I will assign another yield strength equal to 250 megapascal. However, if I'm providing the material with the same grade for all the project, so I will use the same material property. Okay, now let's go to the K. Here, as we said, for direct analysis method, I do not need to assign K value, because if I'm using direct analysis, which means that the K for all my members equals to 1. However, in case I need to design my buildings based on effective length method, so I need to calculate K values, and in this case I need to follow the alignment chart we talked about before, and for a braced frame K will at most be equal to 1. So here, if I'll go to the column, which are the main compression elements, however, K must be applied theoretically for all compression members or any member that has compression force. However, you will see in these rafters that the compression load is less or significantly less than the columns. So basically I'm concerned with the columns. So the K value around the y-axis, which is the red vector here, will be at most equal to 1. So I can assign K for all these columns in the y, Ky equals to 1. However, Kz, which is around the major axis in the direction of the main frame, will follow the alignment chart. When I have a simply supported column, like the end wind column, I will use K equal to 1 for them. However, for released in axial column, because these columns are released in axial, actually they will not be governed by the compression, because the compression will be negligible. It's only due to their own weight, because it's released from the top, so they will carry no compression load from the rafter. So this is just for your information. I will not add any K value now for my building, because I'm using the direct analysis method, which is the most reliable method as per the code. So now I will go to the unbraced length in the design of compression member, and to get the slenderness ratio, KL over R, K equals to 1 in my case, because I'm using direct analysis method, so I don't need to add K. So now L, the unbraced length. So the unbraced length it depends on the bracing I'm providing for the members along their local axes. So let me now show the local axis again for these members. So for the rafter, LZ is for the rafter buckling around the z-axis, which is up and down. So what is preventing the rafter from buckling up and down, which is the vertical supports. So here I'm providing a support for this rafter at the start and at the end, so it will restrain the rafter buckling at the start and at the end. However, at the middle, I don't have anything to prevent the rafter from buckling due to any compression load. These struts are added in plane laterally, so they cannot provide buckling resistance for the frame around the major axis or the z-axis. So LZ for these columns must equal to the full span, which is here 30 meter. However, if I have a column at the middle, in this case, this column will provide a vertical support for this column, and it will brace it against buckling around the major. So the unbraced length in this case, in case I have a middle column, it will be half the span, which is 15 meter. So for now, I need to add LZ equal to 30 meter. And by the way, because I'm providing segments in my rafter, and in case I did not add this LZ, it will treat each member separately. So it will think that the unbraced length for this segment is only the distance between these nodes, 6 meter, 1.53, 6.037, which is wrong, because this will buckle as a whole, as one member with the full length. So for each segment, the unbraced length in the z direction will equal to 30 meter, because it's a one member will buckle at once between these columns. Now, when I have a very steep roof, when the angle of the rafter will become, let's say, very steep, so the angle will be larger. I'll go to 20, 30, 45, 60 degrees. I will see that it will not be this case. I will see that these members, and let me show you to clarify my point, I will see that these rafters, the windward and the leeward rafter, will somehow brace each other at the ridge point. Now the angle here is, assume it's 90, so here it will be 45. In this case, and I can see that from the deformation or the displacement of the rafter, this portion, it will give me kind of restraint for the buckling of the windward and vice versa. However, I cannot rely on this in my design. So if I will do a direct analysis method or first order analysis method, I cannot be sure if it will fully provide this restraint for the buckling, as if I have like a column in the middle, or partially, because it depends on this angle. And if I have an angle which is not very high, it will not provide full bracing for this rafter to buckle with this shape. So umbrella length about the major axis will be half of the rafter length. So what shall we do in this case? Either to conservatively design the rafter with unbraced length around the major axis with the full span, similar to what we are following here, or to perform buckling analysis method. So for now, I will add LZ equal to 30 meter for my columns, for my rafters, and for LY it will be the distance between these struts, because for sure these struts will end at the X bracing here at roof, and after that we'll transfer it to the vertical bracing. So for sure it's a bracing system around the roof minor axis LY. LY here, the buckling of the roof laterally. So these struts which are connected to the braced bay will provide the bracing for the roof at the locations of these struts. And the struts here are at 7.5 approximately. So the umbrella length will be 7.5 for the rafters. Now for the columns are unbraced from base to top, so I don't have any struts here to provide a bracing for this column. So it will be the full length, which is here 7 meter. So if the unbraced length for the column will be the default length of the member, I don't need to add any parameter. Let me assign this for these values for the rafter. So let me select the group, and I will also assign ly value, and here we go. Now regarding the bracing, the X braces for my building, I also need to assign ly and lz for these members. So let me first of all select these members, and then I will turn on the local axis for these members, and as I can see here, we have two buckling planes, in plane buckling and out of plane buckling for the X brace. So by looking at the vertical braces here, I can see that the in plane buckling is around the z-axis, and I will recall the green instead is the z-axis, which is the major axis mainly for the members. The y is the red axis, which is the minor axis for the members. I'm talking about members where the both axes are not symmetric, like I-beam or angle. However, when I have a tube or pipe, I will have symmetry in around both axes. So the minor will be the red axis, and the blue is the longitudinal x-axis. So now let us start with the in-plane buckling for the vertical brace. It will be around the z-axis. So if I take just a step here and show you the in-plane buckling for these members, it will be around the intersection point of these two braces, which means that the unbraced length for these braces is half the total default length because I drew these members without the intersection point. So when I want to assign the length for in-plane buckling, which means the LZ, it will be half of the full length of these braces. Okay. Now regarding the horizontal brace, the in-plane buckling is around the Y, as we can see here. So in this case, these braces will buckle in plane around the Y local axis. So also, the unbraced length for these braces will be half the full length, which is here around 11. So the unbraced length will be 5.5 for LY now for the horizontal braces. Now what about the out of plane buckling? So I have in plane buckling, which I just showed, and I have out of plane buckling. Out of plane buckling, which means that this brace, the horizontal, will buckle around the z-axis, up and down, and the vertical brace will buckle around the y-axis, right and left from this view, right and left, out of plane of the brace. So what are the unbraced length factor or the unbraced lengths I need to assign in the parameters? Now the AISC code appendix 7, it gives me that statement in the commentary of appendix 7. It says that the effective length may be taken as 0.5 L for both in-plane and out-of-plane buckling of concentrically loaded compression braces in X-braced frames, where L is the overall length of the brace between work points with identically sized brace members, which means here I have a condition that these bracing members must be identical in section. Also, the compression and the tension braces are attached at the midpoint, and the magnitude of this compression and tension force are approximately equal. However, if these conditions do not apply, I can expect greater unbraced length for out of plane buckling. What does the code say? The code say that here I have in plane buckling, which is typically half the length of this member between the working point, the base and the top. However, the out of plane buckling, it's a bit more critical, because if I can see here, I have an intersection point between the two braces, and this intersection point will also provide stiffness or some sort of bracing for out of plane buckling of these two braces. Okay. However, this is not always the case, because here I can say that for ideal case, I have both braces with the same stiffness, same profile, and also the compression and the tension forces are approximately equal. So for my case, I can expect this to happen. However, if the case that I have both X bracing are not equal in profile and stiffness, then I need to increase the out of plane buckling for these members. So what is the value used? The practical common value is 0.7 of the full length of the X braces member for out of plane buckling, and this is mentioned in some codes. As I recall, the British code, the old British code, and the Egyptian code, and also this can be further verified by buckling. So this is more conservative if I used out of plane buckling for these X braces to equal 0.7 rather than 0.5. And this is what I will follow in my example now. So the practical side, and this is also verified in other codes and adopted after verification, that the X bracing out of plane buckling will equal approximately 2.7 of the full length. However, this statement in the code is still applicable after I verify both conditions. So let me start with the assignment here. I have the full length divided over 2 for in-plane buckling for the horizontal brace, and it will be multiplied by zero point 0.7 for out of plane buckling conservatively. So I'll start. Define. Now Ly for in-plane buckling for the horizontal brace, it will equal 11 over 2, which is around 5.5. And the LZ here, I forgot to assign it for this brace. I will do it again here. And for the out of plane buckling, which is LZ, it will be 0.7 of the full length, which is around 7.7. Now for the vertical, the in-plane buckling will be around the z-axis. So I will assign LZ, which will be half of the full length, 5.32. And Ly, it will be 0.7 of the full length. Okay, so now let us move to the next parameter, which is main here. Main is the allowable slenderness ratio L over R. And this value, as per the code recommendation, will equal to 200 for compression members, and for tension member, here is listed as T main tension slenderness ratio is around 300. This is to be followed. However, it's recommendation in the code and it's not an obligation. And also, if my member is not actually under axial compression or tension, like the end wind columns, I can increase this value of the slenderness, especially for the compression. So either to use 300 for the compression, or I can increase it when these members are not carrying the load. And if the code tells me that I have a slenderness problem with these profiles, especially in the optimization stage. For now, I will not assign any parameters regarding the slenderness ratio. I will leave them as is now, and I will move to the net section for tension members. So what is the net section for these tension members? It's related to the area net for design under tension load. And as I said before, we have the shear lag factor U, which is related to the connections. And I have a table, and this table is given in the code for different types of connections. Here's the shear lag factor. Depending on the connection between the members, I have different factors for the shear lag, and these are given, and these are not by code, but mainly they are taken from this table to as a general factors for hinged beams, braces, moment beams, and columns. However, I need to mention something, that these recommended values to be used in the design model is when I'm concerned with the connections. So when I'm concerned with the connections and I need to optimize my members with regarding to the openings in the connection, shear connection, for example, or even sometimes I might have some openings for electrical or mechanical, some very small openings. Uh, I might consider also a reduction in the section property. However, because my model here, I'm concerned about the member design and the connection design with the holes and the coping of the flange where applicable. I will design them later with the connection design software. So it will not always be the case with this table. So this table will not mainly govern my members tension capacity because it's related mainly to the connections, as you see here, through plate, double web doublers connected to the other element. All these things will control my shear lag factor and as a result the effective area for tension. Now for me, I can follow this table as a general table, although it's quite conservative because it's also related to the main table, which is concerning the connections mainly. Generally, if I don't need to look at this, you can take this factor conservatively as 0.85 for all my members, because here the braces and the hinged beams can be designed for the connection with the openings for the bolts or the holes, sorry, uh, for the bolts. The columns, generally we don't allow any openings in these columns because they are the main axial members, either in tension or compression. So even drilling in the column to to facilitate any mechanical services is not allowed unless it's verified by modeling, and mainly finite element modeling will work. Other than that, it's not recommended at all. So I will not even add the shear lag factor because the column will be with the full section along its length. So now I can either assign 0.85 for all members except column, or I can use this table. For me now, I will just follow the 0.85 and I will assign it for all. Because as I said, I'm not concerned with the holes in the members at the connections location because all these reductions will be taken in the connection design. So here I will just select everything except of my columns. And I will assign this reduction factor for the tension. And now we have this parameter, which means the output details for my design. So after I input these parameters, I can see the calculations from the code listed in the design output. So I can choose 0. I don't need any design output, or intermediate design output, or maximum detailed design output. I can choose whatever I want. I might choose like 1, and I can assign it for one member. If I need to provide a sample, calculation sample for my report, in case I need to output or have a report, STAAD report, I can provide one sample for one member. Now let's move to the UNB and UNT, and these are the last parameters I will use for my example. And these parameters are related to the lateral torsional buckling for flexural members. So UNB and UNT are basically the lateral torsional buckling umbrace length for the members. However, in the STAAD, this is divided into bracing of the top flange, UN top, and bracing of the bottom flange, UN bottom. Which means regardless if the top flange is under tension or compression, I can provide where I need to brace the top flange, at what interval. And the same is applied to the bottom flange. For example, here, for moment frame, I can expect that the top flange will be at compression at the positive moment location, at the middle portion of the beam. However, near the supports, I can expect that the compression flange will be the bottom flange. So because the lateral torsional buckling is concerned with the compression flange, regardless it's top or bottom, this will control my design for LTB, lateral torsional buckling. However, as I said here, I can provide the bracing for the top and the bottom regardless where is the compression flange. So it will facilitate my selection for the parameters. So now let us go back to the lateral torsional buckling umbrace length here. Here I'm showing it as LX bar, and here it will be the LBR. So in the calculation for the umbraced for the lateral torsional buckling, it will be LB. LB is the umbraced length for the member against lateral torsional buckling, and for sure I have it always in my equations for F critical, and also the nominal moment for determination of the member capacity. So how to assign this LB? As we said before, for typical steel buildings, we have this detail which is called the flange brace detail. Here I have this purlin bypass running over my rafters, and I need to provide lateral stability against lateral torsional buckling for the compression flange, regardless it's the top flange or the bottom flange. So here I will simply provide an angle and connect it to the purlin and to the bottom flange. So if my compression flange happens to be the top flange, so if it will buckle laterally, this bracing, imagine it as single diagonal brace for braced bay, it will take this force and transfer it to the tension flange, which will be in its place. So it will provide stability for the compression flange. And if my bottom flange is under compression and I expect lateral buckling at the compression flange, this brace will transfer the load to the top tension flange. So this will provide uh, bracing against lateral torsion buckling. For sure, the flange brace needs to be also designed for stiffness and strength as per the requirements of the code here. And this flange brace typically is used each other purlin and each other girth. And the typical spacing of these purlins is around 1 to 1.5 meter. So if I say that I will provide this knee bracing each other purlin, which means the unbraced length for the rafter between these details will equal to 3 meter regarding the rafter and also the columns, because also this detail is applicable to bracing the columns, because the columns also will work as flexural member against lateral load and even vertical load. So now I will provide UN top and UN bottom for the rafter and the column at a distance equal to 3 meter, which is typically each other purlin. This is common rather than to provide this brace at each purlin to reduce the work at site and the quantities of these braces. I can use them each other purlin. Also, for sure, I can increase this uh, spacing between these knee braces. However, typically I will follow this, and now I will go and add these parameters. So I'll select my rafter and the columns, and now I'm done. So after I added all my design parameters, I will go to commands and I will choose check code. So it will check all my members against the selected code with the parameters. Here, show all, assign to view. Also, I can add takeoff command, which means the quantity of the members to get my final tonnage. I can add member takeoff so I can know the weight of each member, or I can add takeoff generally to give me the total weight of the building, which I will choose here, and I will add a sign, and I will run my model to see the results now. Okay, now let us see the results. right click, structure diagrams, design results, and show diagrams, and I will apply. And this is the result of the members. I can see that I have many failed members that I need to uh, change, increase in order to have a safe design. First of all, I have an observation here I want to share with you and how to solve it. As you can see, I have a very high stress ratio for these struts between these braces. The reason behind that, and as I can see, as I'm moving further from this region, the ratio decreases. So, what is the reason behind that? I can double click on one, and I can see here I have a high compression force coming from load 17. If I go here, I can see that the compression force is much less. Okay, so I have a concern here, and I can verify it further. As I said, it's load 18 or 17. Okay, I'll go to load 18, and I'll see which is or which load cases does it have. Here it's 3, which means dead 1.2, 4 roof live by 0.5, and 9, which is the temperature, by 1.2. I'll go again and see the axial load in my structure due to temperature. You can see here that due to the temperature load, I have like force trapping. So these members are trapped between two X braces, and they are having a very high force due to the temperature. So this might happen sometimes, and the best way to solve it is either to have one brace and to increase the members of these braces to attract all the forces coming from one direction, or to have like expansion joints between several uh, uh, stations. For example, if I have this building 80 meter, at 40 meter, I will have an expansion joint, and this can be done by providing releases. So here I have release in the X, so I will select one bay here, and I will provide this release at one side, axial release. As you can see here, this bay now is axially released, so I have like an expansion joint between this portion and this portion. In this way, I will dissipate this force between the braces, and I can expect lower forces. So, as I said, this force is not coming from lateral load like seismic or wind. It's coming from the trap of the temperature. So I will run the analysis again and see to see if this problem is solved now or no. Okay, I will once again show the results. You can see here the problem is solved, and I can also verify that by showing the axial load. All the axial load in these struts now uh, almost disappeared or become much less. So in this case, I can continue with the design for the members. Now let us see here. The columns, the main columns are stressed 1.14 approximately. And the design, it's telling me that the critical location is at 7, location at distance equals 7 from the start. I have an axial force equal to 215 compression C. My is negligible for sure because out of plane I don't have forces, I have bracing, I don't have moment frame. And the mz flexural load is around 1073 kilonewton. The ratio is 1.1, and the critical equation is H11, which is the combined axial and bending on the member. So what does it mean? I need to increase my profile, but how to increase it? Shall I increase the thickness of the web, or the thickness of the flange, or the depth of the section at the top, or the width of the flange? So I can expect that the failure in my member is due lateral torsional buckling. And in this case, the best way to solve this is to increase the width of the flange. So if I increase the depth of the flange, it will not be that efficient, but increasing the width will be much better. So it's a trial and error process. Here also, I have the a similar issue for the beam. So this region and all the frame for sure, I need to increase the profile. Here also, I have it at distance equal to 6 meter. So also at the end here, mainly at the positive moment. If I look at the moment diagram, for example, due to gravity load, I can see that the moment here is positive. So let us go and try to optimize. And first, I'll go to the properties and I will change the sections. So if I need to increase the section, but I'll try first to change the depth of the profile. And why is that? I don't need to increase the section area much in order to reach an optimized section. I'll try. If it works, then okay. If it doesn't work, I will go and increase the width of the flange. And always better to increase the length or the width rather than to increase the thickness. It will help you much with the optimization. So I will try now with 85 centimeters, and I'll do the same with the rafter. And let me now also increase the section at the middle. I'll make it also 35 centimeter. Here to the apex, I can rather increase it to 70. So from 35 to 70, and I can see it at the rendered view. So let us see if this will work or no. I will run the analysis again to see the impact on the results. I'm starting now with the main frame. After that, for sure, I will move to the struts and the braces to solve their issue as well. Okay, I can see that increasing the depth did work for me, and in this case, uh, I don't need to increase the width of the flange, but I will just make a trial. You can see now the ratios, 0.9, 1.925. I increased the depth of the section by 15 centimeter, by 15 centimeter. So I just want to make a trial to show you the effectiveness of the increase in the flange width, because it will help me with the lateral torsional buckling more than the increase in the depth. I'll do that only for the members at the corner. And let us see the result. This is in case that increasing the depth is not helping me. I can go to increase the width of the flanges, because yes, increasing the depth will increase the inertia of the section in case it's failing under yielding. However, if it's failing under lateral torsional buckling, increasing the width of the flange will help me more. You can see now that the ratio decreases by increasing the flanges only 5 centimeter, rather than to increase the depth of the section by 15 centimeter. However, I can do a quick check to see what option will save me more material. So here I will increase the section by 15 centimeter, 15 by 8 millimeter, so around 9 kilogram. However, if I go to increase the width of the flange, I need to increase the tonnage or the weight of the section 15 kilogram. This is per meter. So, which means that increasing the depth of the section will be more economical for me, and you can do that by yourself. You'll see that increasing the depth of the section will be more economical for me. I will go now for increasing the depth rather than to increase the flange. It's simple. Just you will multiply the difference between zero point 0.7 and 0.85, 0.15 by 0.008, because you are increasing the web and the web thickness is 0.008, by the density of the steel. You will get around 9.4, okay, kilogram per meter. And if you go to increase the width of the flange from zero point 0.2 to 0.25, you will have an increase by 0.05 multiplied by the thickness of the flange, 0.02 by two flanges, because I have two flanges, by 2 by the density of the steel, you will have around 15.7 kilogram per meter. So increasing the width of the flanges will result in more area or more tonnage than increasing the depth. So, however, it's more efficient as well, especially in resisting the lateral torsional buckling. So if this doesn't work, I'm increasing the depth and it's becoming very large, or I have a problem with the clear height or the floor height, architecture floor height, I will go and increase the width of the flange. It will help me uh, in much better way. Okay, maybe here I saw that I still have a problem with the positive moment. So at the middle, so I can further go to point 8 to see if it will work with me. And I will run again. For sure, after I get my section safe, I need after that to go and check the serviceability limit states. So it's trial and error process. It can take you a little time if you chose uh, a closed section from the beginning, or it can take you more time, especially if you have a complex structure and many members. It can take you more time. However, eventually you will reach the uh, most optimum design by doing these trials and errors. However, as we said, because we have a theoretical background, we know that increasing the width of the flange for the flexural member will help me much more than increasing the depth, because as we said, for lateral torsional buckling, the buckling of the compression flange laterally, which means around its major axis, uh, will be critical. So now I have all the members safe and the ratio is pretty high. I have a very optimized design here for the main frames. Here slightly I have slight failures in these members. It's 1.02. So let me, I can now, for only for these frames, I can increase the properties, or I can do that for all now. Let me do that for all. So the problem might be with the frames. So I will a bit increase the depth again, or I can separate them as I said. But now if I need to have an optimized design, or sorry, a uniform design, I'll do that for all. And I'll go back to check the braces after I finalize the design for the main frames. Always try to increase the depth or the width of the section rather than to increase the thickness. It will help you with the tonnage, and most of the time it will be more efficient. Okay, so now my design is safe for the main members. Let me see the uh, struts. You see the struts, the main issue is the slenderness here. So the main issue I'm facing here is not the capacity of the member, it's the slenderness. And as I said, it's a recommendation. So if I see that the compression force is not that high in the brace, the strut, so if I just slightly increase the slenderness ratio from 200 to 210, it will be okay. Let me see also for the X brace. I think I have the same issue here. It's the slenderness. So it's failing not because the section itself cannot carry the load, but because I'm exceeding the slenderness ratio, which is at the end a recommendation only from the code. So I can rather increase these members, but as I can see here, the failure is really minimal. So I can just use the slenderness, especially if it's not like a must in the code. And also, I'm not that far from the ratio, so I can go for it. And at the end, it's left for you. Some reviewers, if you are working with like a designer or a contractor, and you have a reviewer, third-party reviewer, either it's a consultant or it's a client representative, might not accept, and he will say, just follow the code recommendation. I prefer to follow the code recommendation. Then you will have to follow the code and stick to the 200 limit for the compression member slenderness. Now let me run the analysis once again, and I will not go for further optimization of the end wind column and the overhangs that you can do by yourself. You can just go and change the profile to see if it's adequate or no. So I will leave it for you to gain time. Once again, let me check the results. And everything is okay now. For sure, you can do optimization for these end wind columns, but as I said, I will leave it for you. So let us now go and check the serviceability again. So before I check the serviceability, I need you to know something, that this is a direct analysis method, and the direct analysis method is providing reduction in the stiffness for the members. So for this reason, all these values I got for the deflection of the members and drift are larger than the actual values on my structure. How to solve this? I can multiply all these results by the reduction factor I did to the members. So in this case, I will result in unreduced sections, check against the drift values. So before I go and multiply these values by the 0.8, and this is only when I'm using direct analysis method. Other than that, you can go and uh, change the analysis method you are using by choosing P delta analysis. In this case, you don't need to multiply the displacement or the deflection values by 0.8 because I don't have a reduction on the material in the P delta analysis, for example. Okay. However, now I don't need to redo the model again or change the analysis again. I will multiply my results for the deflection by 0.8 to check the serviceability limited states. Before that, I can just facilitate things for myself, and I will add the serviceability combinations and check them directly. So I will add them manually this time. I will call it serviceability 1, dead load plus roof live load. So I will have dead load here and roof live load, and I will add. Let me now go to the command file. I see my serviceability combination at the end. However, I will add the repeat load because I'm using second order analysis, so I need to use the repeat load here. I can also separate these combinations, and I will put a note here, serviceability combination. So they will not be part of my design. My load list is up to 150. Only these are for the design of the members. These are for the check of the serviceability. Let me now get all the needed combinations, and I'll go back to the serviceability slides, and I can see for members or roof members supporting non-plaster ceiling, which is my case, I have the limit for dead plus live equal to 180. Snow or wind for the roof members 240, and live also 240. Now for the walls, I have for walls supporting metal siding H over 90. And what are the combinations? As I said here, dead plus live or roof live. In my case, it's roof live. Roof live, I have it already. And dead plus snow, I don't have snow load. So the final one I need to consider 0.9 dead load plus 0.45 wind load. And I have how many cases for wind? I have 4 cases for wind. So I need to add additional 4 cases for the serviceability for the wind. I have now 0.9 dead load plus wind load 1. So also I will use the repeat load. I will only change the loads or the load cases in it. So I will go and start with the dead load 0.9, 3 here, which means load case number 3, which is here the dead load and the factor. Now the wind, which is 5 here, and the factor will be 0.45 because I'm using ultimate wind. And then I will carry on with the other wind load cases 6, 7, 8. So I will do that again. I will call this 51, 52, 53, and 54. Wind load 1, 2, 3, and 4. And here I have it 5, 6, 7, and 8. Okay, and because I'm using now the repeat load, I need not to use load combination to be only uh, like load 155. Other than that, the software will not understand it because the combination does not have with the repeat load. So save and exit, and I will check the combinations now for the serviceability. I don't need to check the seismic drift, and it's for the design for seismic, because as I can see, it's mainly governed by wind, and the seismic load is much less than the wind base shear at my building. However, if it's not the case, I will go and check the drift due to seismic. So okay, here let us look at the results. I have the eave height equal to 7 meter. So 7 meter over 90, sorry. So I have an allowable displacement limit laterally equal to 7,000 over 90, which is equal to 77 mm. However, here the maximum value I have, which is 30.3 multiplied by zero point 0.8, because I need to remove the reduction from the direct analysis. So I have maximum of 24.24, which is much less than the limit. So I don't have any issue with the drift. And in the z direction also, the drift limit is also much less. Now for the deflection, the vertical deflection, let us check first the roof live load alone. Here the roof live load is 104. I will multiply 104 by 0.8. So the actual deflection I have is 83 millimeter. So the allowable against the roof live or live will be L over 240, which is here 30 meter, over 240, which is 125. So it must not exceed 125. And what I got is 104 multiplied by 0.8, which is 83. So it means that it is safe. Now the dead plus live, 231, and my limit is 30,000 millimeter over 180. Now I have 167. 167 is the allowable, which is the span over 180 here. However, in my case, I have 231 multiplied by 0.8, which is 184. So I have around the 20 mm exceedance in the deflection, in the allowable deflection. So I have a problem here and I need to solve it. Okay, let me just write them down again for you so you don't get confused. Here for 0.9 dead plus dead load plus 0.45 wind load. Here I just need to adjust the name in the command file. I will not now it's 0.45. I already assigned, as you can see here, 0.45. However, I need just to adjust the name, but I will not interrupt the run and do it again. So the maximum now I have it 30 without reduction. With the reduction, or sorry, it's 30 with the reduction. Without reduction, 30.3 multiplied by 0.8, which is here 24.3. This is the actual that I have. Now for roof live load, it's 104.6. So I will 104.6 multiplied by 0.8. I'll have 83.7. And now for dead load plus roof live load, I have displacement. I can see it here. You can see it's highlighted on the 3D view. 231.5 multiplied by 0.8, because I'm using direct analysis, I have it 185.2. The allowable values now for the vertical, these are for the vertical and this is for the drift. For the drift, the allowable equal to the height 7000 mm over 90, which is 77 mm, which means that I'm okay. And for the roof live load, the allowable deflection is the span, which is 30 meter over 240, which is 125. And for the dead plus live, the allowable is over 180, which is 167. For the dead plus wind, it's 73 mm. If I need also to check dead plus wind, it must be less than L over 240. However, I can see that it's far from the limit, 73, and dead plus roof live is controlling here, and it's much higher. So, however, if I need to check it here, it's 73.7 multiplied by 0.8. I have around 59 mm, and it's checked against span over 240, so 59 mm for sure is less than 125, the limit, the allowable limit. Okay, so what can I do now for the dead plus roof live? I can use camber, or I need to increase my stiffness of the members, which means I need to increase the inertia and the section profile. But if I don't need to do that, I can only increase, or I can limit this deflection by using cambering at the mid span. So what is the camber value? I will go and select the dead load, which is here 123 multiplied by 0.8, which is around 98 mm. So I will do a camber at the midspan with 80% of the maximum deflection under dead load only, which is 98 by 0.8. So I will do a camber to around 78 or even 70 mm is enough. So now, if I do a reversed camber, I will 185 minus 70. I will result in a final deflection of 115 mm, because the camber is upward for sure, which is less than the allowable 167. So in this case, I will just mention on my drawings that I have an upward camber at the middle equal to 70 mm. So now I can say in confidence that my structure is safe, strength wise and serviceability wise. And this is my structure here. I will read the output, the tonnage for the structure, and it's 57.7. If I need to get the tonnage, I will divide on 9.8. So as a result, I will have around 58 or 59 tons for my structure.